Hello, I'm Richard Pitwon. I'm notorious for cramming a huge number of slides into a short amount of time, but I'm being very good now. So I'd like to quickly acknowledge, my name is Richard Pitwon, I'm CEO of Resolute Photonics. Thank you very much for the invitation, OCP. It's a real pleasure to be presenting at the inaugural session for Quantum, so I'll see if I can answer some of the crucial questions. I'd like to acknowledge our co-authors on this paper from Senko and from National Physical Laboratory in the UK. So let's start with optical interconnect and hyperscale data centers. Won't be any surprise to you, hyperscale is now the dominant form of data center since about 2 years, and optical interconnect is intrinsic to multiple tiers within the data center. So rack to rack, of course, for decades, but now certainly in OCP here we're seeing the migration of optical interconnect into the enclosure with the CPO and schemes like that. Fundamental question, because this is the inaugural session, why is everyone getting so excited about quantum? What's so strategically important? It's still a tiny market, and it'll be a tiny market for a very long time. So why is it important? Well, it can be best explained by something called the Moscow equation. A very simple equation has three variables. I'll start with the last one, Z. Z is the amount of time it'll take from now to a quantum computer, a useful quantum computer being created. I know there are quantum computers now, but I mean a useful one means you need a certain number of qubits to be able to carry out useful functions. So that's Z. Y is the amount of time it'll take us to develop quantum-safe networks. So networks where you can tell if your data has been intercepted using schemes like quantum key distribution. And X is the amount of time after we send our data, after which we don't care if it's been hacked. And the problem here is that we send data, it's encrypted, and we have to assume our adversaries have intercepted it, they've stored it. They can't decipher it yet, but they store it and they can decipher it later when they have a quantum computer. And that's what people are terrified about. The Moscow equation says basically if X plus Y is larger than Z, worry. It means our adversaries can hack our crucial data. And that's what's driving this. So where does hyperscale fit into this? Well, what I love about hyperscale data centers are they are a microcosm for all sorts of advanced technologies, and quantum is no exception. Quantum computing will be a valuable resource. We foresee pockets of quantum computers in hyperscale data centers. IBM have that already, where you have quantum as a service, where you outsource quantum computers to solve those very specific problems which classical computers can't address. They won't overtake digital computers ever. The hyperscale data centers will always be 99% digital, but you need quantum computers increasingly to solve certain specific problems. And so they'll be crucial. And also on the edge of data centers, when you're sending crucial information out of the data center, you need to have QKD, quantum level encryption. So it's important for data centers. So I'm going to talk about international standardization of quantum interconnect. This is very important, especially for OCP. There's been a lot of activities over the last 5 years, scattered activities shown here by different standardization organizations to attempt to create standards for different aspects of quantum. Most of the standards are around protocols for quantum key distribution. But what I did over the past 3 years is I organized a series of cross-standards development organization symposia that brought together the main standards organizations in the world, ITU, IEC, ISO, IEEE, and others, bring those standards people together to listen from stakeholders in quantum and ask them the question, where do we need standards in quantum? We don't want standards to be to stifle innovation. Where are they useful? Where are they not useful? And we ask this question for all sorts of things: quantum transport, terminology, and we learned a few interesting things. One very important thing, which hasn't been addressed in standards so far, is no one's looking at the quantum physical layer, the physical layer. What do we need? What networks do we need to convey quantum data? Well, one important thing is quantum-grade interconnect. A lot of QKD schemes rely on single photons. When we're in normal communication, you send a pulse of light, it's comprised of millions of photons. In order for these quantum effects to work, these effects which allow us to tell if our data has been intercepted, we need to send a single photon or a pair of entangled photons. And so that single photon has to go through this obstacle course of different connectors, glass fiber, which has imperfections and impurities, and it has to reach its destination, and that's crucial. So that means we need the current standards for connector losses are just they're still too lossy. They're designed for the pulses of light, which have millions of photons in them. We need new standards for very low loss connectors, quantum grade connectors. We need new types of fibers. We need new types of components. So quantum grade connectors here, for example, we need components such as arrayed waveguide gratings, which allow us to bypass quantum single photons from things like erbium-doped fiber amplifiers. So we can send quantum and classical photons along the same channel. And we need new types of fibers. I mean, existing fibers are plateaued, they're the best they can be, but we have some interesting new types of fibers. For example, Luminicity, which was bought by Microsoft not too long ago. They have a hollow core fiber which is lower loss than even normal fiber. Incredible, great potential for quantum. Anyway, so quantum grade interconnect is important. A year ago, we published results here for a quantum grade connector. You see. This is no TDR. This shows you the loss. This dip here is a splice connection. But what we have is two quantum grade connections. No, sorry. So the splices are here, but a quantum grade connection is here, almost seamless. You can just see a tiny dip, and that's important. We need to look at extremely low loss optical connectors, and they can be made. Now here I introduce the IEC, International Electro Technical Committee, one of the three international standards bodies, and one of the largest technical committees there and mainstream committees is TC86 for fiber optics, and it deals with all aspects of fiber optics. A subcommittee A for dealing with fibers and cables, subcommittee B, which I chair, which is optical connectors, and subcommittee C, which is about active devices such as sensors and photonic integrated circuits. Photonic integrated circuits, you probably know, but just to give you a quick summary, those are integrated circuits in which the structures can guide light and change the speed of light. And if you control these two capabilities, you can do anything. You can modulate, you can split light, you can turn it on and off, you can route it and change the ratio. Common platforms for this, silicon photonics. Silicon is the most common, and you will have seen a lot of that today. Indium phosphide, silicon nitride, silica, glass, electro-optic polymers, lithium niobate, and barium titanate. These are all, or many of the platforms which are used for PICs. Now, PICs, the largest application today is optical transceivers, as we've seen, but you have other applications, WDM switching for telecom, neuromorphic computing, wearable diagnostics, so Rockley Photonics and others who are looking at non-invasive blood monitoring. This is also important. Sensors, LiDAR, many LiDAR solutions use PIC, and increasingly certain quantum technologies, including quantum compute. So PIC technology is critical. So one of the other findings of these cross-STO symposia is looking at quantum photonic integrated circuits, the kind that the previous speaker was talking about. These are important. Where are standards useful there? Well, benchmark standards are useful. How do we couple fiber to QPICs? The losses today are, 0.5 dB is way too high. We need to find very new ways of coupling to QPICs, which are, less than 0.1 dB. So those kind of questions are very, very important for standards. In the IEC, we are preparing the first technical report for quantum technologies, and that's actually quite important in this technical committee because it will lay the foundation for the first real quantum standards in the IEC. A very quick introduction to two European projects. One is Dynamos, which started last year. Now, Dynamos is about hyperscale data centers, and it is looking at various technologies, fast tunable lasers, AWGs, arrayed waveguide gratings, efficient electro-optic modulators. And the purpose there is to look at WDM to create new architectures for data centers. Adoption is another similar project which started before, and it's looking at new types of co-packaged optics. I won't go into detail. But the point is, increasingly we're seeing the next generation of this, looking at having quantum PICs on disaggregated networks at the fabric, at the module, at the enclosure, and at the chip level. So more about that in the future. But I just wanted to give you a taster. So in conclusion, quantum technologies are becoming a mainstream technology, and they're driven by the need for information security primarily, computations, new types of sensors, advanced metrology. But quantum networks require low-loss interconnect and associated standards. Thank you very much.
Thank you, Richard. My first question, how many slides was that?
That was 26.
All right. Any questions from the floor? Yes.
Richard, thank you. Good content. So you talked about low losses on the connectors. How low is low that you have seen or required for the levels that we're talking about?
Well, some of the losses that are reported were lower than 0.05, and you can go even lower.
Randomated connectors.
Yes, that's right.
Cool. Thank you.
Any other questions? One question, Richard. Okay. For quantum peaks, it is a peak basically a design for quantum application. What is the key challenge here? What kind of the peak that you think that is most essential for quantum application?
Well, if you take one of the one mature type of quantum peak, a quantum random number generator, it requires manipulation of single photons. So again, it's not millions of photons in a pulse; it's single photons. So the key challenge is loss on the waveguide. Silicon nitride, for example, is a preferred PIC material for quantum because it has the lowest loss over a broad range of wavelengths, and coupling to the chip is critical. Edge coupling in the case of silicon nitride is basically the only viable solution to get really low loss. And I think Quantum have reported extremely low losses for that in cryogenic environments. So there are ways to achieve very low loss fiber to PIC coupling. So it would be the loss because you're manipulating entangled pairs of photons or single photons.
Okay. Well, in order for quantum computers to work in a real environment, it would need to be above cryogenic. Is there any effort right now in standardization for increasing the temperature of operation?
Yes, well, not in terms of not standardization yet, but technologies are being developed to make it room temperature. Areas where you probably need cryogenics like simple like 4K to 10K, the kind of off-the-shelf cheaper cryogenics, not the chandeliers that you see with IBM, but the more manageable rack scale ones, which would require cryogenics, are high fidelity quantum sources and superconducting nano receivers. I foresee needing those in their own cryogenic chambers because that's the fuel. That's the fuel you need. But other things, the PICs that process them, they don't need to be in cryogenics. So you can couple out of the cryogenic chamber. You can couple these deterministic single photon sources out, and process them as appropriate. But I don't think cryogenics is that wieldy, but high fidelity sources are critical, and cryogenics helps with that.
All right. Thank you, Richard. Any other questions from the floor? If not, thank you very much, Richard. Thank you.